Welcome all. Today's topic is continental drift and plate tectonics. The theory of continental drift is an attempt to explain the present arrangement of continents and ocean basin. In this theory, it is presumed that in the geological past, all the continents were united. The united and parent continents was called as Pangaea. The Pangaea, however, started breaking up near the close of the Mesozoic era. The idea of continental drift is very old, and the correspondence between the coastline of Africa and South America appears to have been known to the most of the explorers and navigators of the Great Age of Discovery. As early mapping gained accuracy, some observers noticed a symmetry in the western coast of the Africa and the eastern coast of South America. Abraham Ortelius described the apparent fit of some continental coastline in his Thesaurus Geographicus, written in 1596. In 1620, the English philosopher Sir Francis Bacon noted gross similarity between the shape of Africa and South America. Soon after the first reliable world maps were made, scientists noted that the continents, particularly Africa and South America, would fit together like a jigsaw puzzle if they could be moved. Antonio Snider Pellegrini, a French, was one of the first to study the idea in some depth. In his book, Creation of Its Mysteries Revealed, he showed how the continents looked before they separated. Alfred Wegener, a German meteorologist and geophysicist, publicly presented a lecture his idea that Earth's landmass migrated. His book Origin of Continents and Ocean appeared in 1915. Wegener, who is today regarded as the father of this concept, based his theory not only on the shape of the continents but also on geologic evidence such as similarities in the fossil found in Brazil and Africa. He drew a series of maps showing three stages of drifting process, beginning with an original large landmass called the Pangaea. Wegener believed that the continents composed of light silicic rock somehow plowed through the denser rock of the ocean's floor, driven by the force related to the earth. Pangaea, meaning Pan means all, Gaea means earth. Pangaea is a hypothetical continent from which the present continents originated by drift from the Mesozoic era to the present. Wegener hypothesized that the supercontinent of Pangaea broke up to form Eurasia, which includes North America, Greenland, and all the Eurasia north of Indian subcontinent, and Gondwana land, which consists South America, Africa, Madagascar, India, Arabia, Malaysia, East India, Australia, and Antarctica. These two blocks were separated by a long, shallow inland sea called the Tethys Sea. According to Wegener, the Pangaea was surrounded on all sides by an extensive water mass called the Panthalassa, means Pan means all, Thalassa means ocean, or the primeval Pacific Ocean. Wegener also assumed that in the Carboniferous period, the South Pole was near Natal, that is in South African coast, and the North Pole was in the Pacific Ocean. According to Wegener, the Pangaea started breaking up in the Carboniferous period, that is about 300 million years back, and the present shape and relative position of the continents are the result of fragmentation of Pangaea by rifting and drifting apart of the broken land masses. He was also of the opinion that the continents are made up of Ciel and the ocean basin are made up of Sima. Ciel, being lighter, is floating over the denser Sima. Direction of drifts. In the opinion of Wegener, the continents drifted in two directions. One towards the equator and second towards the west. On account of the equatorward drift, Africa and Eurasia were pushed closer together and the TTC deposits located in between the two were raised up in the form of mighty fold mountain of Alps, Altias, Tian Shan, Zagros, Hindu Kush, Himalayas, etc. The peninsula of India and the Africa were separated from the Antarctica and Australia because of the equator drift. The reason given for this movement was the gravitational attraction exerted by the Earth's equatorial bulge. The other movement of the Earth was towards the west. This western movement in his opinion was due to the tidal force of the moon and the sun on the continents. On account of this westward drift, North America and South America got separated from Europe and Africa, and the Atlantic Ocean came into existence. In addition to this, Wegener attempted to explain the problem of formation of fold mountains with the help of drift theory. As stated above, on account of movement of Gondwana land towards the equator, that is, on account of their coming closer together, the southern landmass, that is Gondwana, pressing against the northern, the Alpine and Himalayan range were formed in the tertiary period in the region occupied by the TTC. Similarly, the Rockies and the Andes were formed as a result of the westward drift of the Americas and resistance offered by the rocks of the ocean floor to this movement. Between the two immense rafts, a trail of fragments was left behind to form the islands of the West Indies. Wegener assumed that the disruption of the southern block of the Pangaea, that is Gondwana land, took place mostly during the Mesozoic era, while the westward drift of North America occurred during the Tertiary period. Evidence in support of continental drift. In support of his theory of continental drift, Wegener gathered geomorphological, climatological and paleontological evidences. Some of the important evidences given in support of the theory are: first one, geographical similarity in the opposing coast of the Atlantic Ocean. The outlines of the coast of two sides of the Atlantic Ocean are such that they can be easily joined together, and one appears to be the detached portion of the other. The eastern coast of the South America, that is Brazilian Bulge, can be fitted against the western coast of Africa, that is Gulf of Guinea. This was called the jigsaw fit on the opposing coast of the Atlantic Ocean by Wegener. Next, paleontological evidence. The striking similarity of certain fossils found on the continents on both sides of the Atlantic Ocean is difficult to explain unless the continents were once connected. The fossil record indicates that a new species appears at one point and disperse outward from there. Floating and swimming organisms could migrate in the ocean from the shore of one continent to other, but the Atlantic Ocean would present an insurmountable obstacle for the migration of land-dwelling animals such as reptiles and insects and certain land plants. The fossils of Gossopteris, a fern-like plant, have been found in the rock of same age from South America, South Africa, Peninsular India and Australia within 480 kilometers in the South Pole in Antarctica. Mature seeds of these plants were several millimeters in diameter, too large to have been dispersed across the ocean by winds. The simultaneous presence of Gossopteries on all the southern continents, therefore a strong supporting evidence that the continents were connected. The distribution of Paleozoic and Mesozoic reptiles provide similar evidence, as fossils of several species have been found in the now separated southern continents. An example is mammal-like reptile belonging to the genus Lystrosaurus. This creature was strictly a land dweller. Its fossils are found in abundance in South Africa, South America, Asia and Antarctica. The genus thus inhabited all of the southern continents during the same geological period. Clearly, these reptiles could not have swum thousands of kilometers across the Atlantic and Antarctic Ocean. So, some previous connection of the continent must be postulated. A former land bridge similar to present Central America would explain the presence of Listosaurus in the distant parts of the world. But survey of the ocean floor show no evidence of such submerged land bridge. Evidence from the structure and rock type. A number of geological features end abruptly at the coast of one continent and reappear on the facing continent across the Atlantic Ocean. The folded mountain range at the Cape of Good Hope at the southern tip of Africa trend from the east to west and terminate sharply at the coast. An equivalent structure of the same age and style of deformation appears near Buenos Aires, Argentina. The folded Appalachian mountains are another examples of similar geological features. The deformed structure of the mountain belt extends northward across the eastern United States and through Newfoundland, terminating abruptly at the ocean. They reappear at the coast of Ireland and Britain. Other examples could be cited, but the important point is that the continents on both sides of Atlantic fit together not only in outline but in rock types, basalt, plateau and structure. They are related much like matching piece of torn newspaper. The geological similarities on opposite sides of the Atlantic Ocean are found not only in rocks older than the Cretaceous period, which began about 144 million years ago. The continents are believed to have split and begun drifting apart in a Jurassic period about 200 million years ago. Evidence from glaciation. During the later parts of the Paleozoic era, that is about 300 million years ago, glacier covered large portion of the continents in the southern hemisphere. The deposits left by these ancient glaciers can be readily recognized and striations and grooves on the underlying rock show the direction of which the ice moved. Except for Antarctica, all the continents in the southern hemisphere show no trace of glaciation during this time. In fact, fossils of plants indicate the tropical climate in that area. This evidence is difficult to explain in context of fixed continents because the climate belts are determined by latitude. Even more difficult is to explain the direction in which the glaciers moved. Regional mapping of striation and grooves indicate that the South America, India and Australia, the ice moved inland from the ocean. Such movement would be impossible unless there was a landmass where the ocean now exists. Paleoclimatic evidence. Wegener also concluded that the large mid-latitude coal deposit which stretch from North America to Europe to China and date to the Permian and Carboniferous period, that is 245 to 360 million years ago, existed because these regions once were more equatorial in location and therefore covered with a lush vegetation, and that became coal. Evidence from other paleoclimatic records. Other evidence of striking climatic change recorded in the stratigraphic record tends to support the drift theory. Great coal deposits in Antarctica show that abundance of plant life once flourished on the continent, now covered with ice more than 2 km thick. On the other continents, salt deposits, formation of wind-blown sandstone, and coral reef provide additional clues that permit us to reconstruct the climatic zone of the past. The paleoclimatic pattern are baffling with the continents in their present position, but if they are grouped together in their present position, the pattern are easily explained. Polar wandering. According to Wegener, there has been change in the position of the poles in the different geological periods, which he called polar wandering. During the Silurian period, the North Pole was 14 degree north, 124 degree west, and South Pole was near Madagascar. In the Carboniferous period, the North Pole was at 16 degree north latitude and 147 degree west latitude, and the South Pole near Durban, while during the Tertiary period the North Pole was at 51 degree north latitude and 153 degree west longitude, and the South Pole shifted to the south of Africa. The above evidence for the theory of continental drift were considered and debated for years. Wegener was criticized for failing to explain what forces would permit continents to plow through ocean of rock. The idea of moving lithosphere was yet to come. Wegener was dismissed as the crank. His critics claimed with some justification that he had carefully selected only for those data supporting his hypothesis, ignoring contrary evidence, where for instance were the wakes and tracks through old seabed that the migrating continents would leave. By 1926, the drifters were in full retreat. When Wegener died on the expedition across Greenland in 1930s, theory was already in eclipse. Revival of the idea of continental drift. Despite all these opinions and commissions, the theory of continental drift is nearly universally accepted as an accurate model of the way the Earth's surface evolves. At present, all Earth scientists accept the fact that continental masses drifted in a dramatic way, referred to as plate tectonics. The concept of continental drift refused to die. However, those neatly fitted continents provide a haunting reminder of Wegener to anyone looking at an Atlantic chart. In 1935, a Japanese scientist, Kyo Wadaki, speculated that earthquakes and volcanoes near Japan might be associated with the continental drift. In 1940, seismologist Hugo Benioff plotted the location of deep earthquake at the edges of Pacific Ocean. This chart revealed the true extent of the Pacific Ring of Fire, a circle of violent geologic activity surrounding much of the Pacific Ocean. Seismographs were now beginning to reveal the worldwide pattern of earthquakes and volcanoes. Deep earthquakes did not occur randomly over the Earth's surface, but were concentrated in zones that extended in lines along the Earth's crust. Benioff, Wadaki, and others wondered what could cause such an orderly pattern of deep earthquakes. Many of the lines corresponded with the worldwide system of oceanic ridges, the first of which was plotted in 1928 by meteor oceanographer working in the middle of the North Atlantic. Notice the old pattern. They form almost as if the Earth's lithosphere is divided into sections. Benioff sensitive seismograph also began to gather strong evidence for a partial molten non-rigid layer of the upper mantle. Radiometric dating of sediments and rocks was perfected after World War II. The technique is based on the discovery that unstable naturally radioactive elements lose particles from their nuclei and change into new stable elements. The radioactive decay occurs at a constant rate, and measuring the ratio of radioactivity to stable atom is a sample provides its age. To the surprise of many geologists, the maximum age of the ocean floor and its overlying sediments was radiometrically dated to less than 200 million years, only about 4% of the age of the Earth. The centers of the continents are much older. Some parts of the continental crust, like Castagenesis, are more than 3.9 billion years old, about 85% of the age of the Earth. Why was oceanic crust so young? Attention quickly turned to the deep ocean floors, the complex profiles of which were now being revealed by echo sounder, a device that measures depth of bouncing high frequency sound wave off the bottom. In particular, scientists aboard the Lamont Geological Observatory Deep Sea Research Vessel (WEMA) invented deep survey technique. They probed the bottom with powerful echo sounder and looked beneath sediments with reflected pressure waves. The overall shape of the mid-Atlantic ridge was slowly revealed. The ridges conformance to shorelines on either side of the Atlantic Ocean raised many eyebrows. Ocean floor sediments were shown to be the thickest at the edges of the Atlantic Ocean and thinnest near the mid-oceanic ridges. WEMA and other research ships also compiled more complete, accurate charts of the submerged edge of continents. At Cambridge University, Sir Edward Bullard used a computer to process these data to achieve the best position fit of the continental jigsaw puzzle piece around the Atlantic Ocean. The fit was astonishingly good. Mantle studies were keeping pace. The first links in the worldwide standardized seismograph network began during the International Geophysical Year in 1957, were beginning to report data from seismic waves reflected and refracted through the planet's inner layer. This information verified the existence of a layer in the upper mantle that caused a decrease in velocity of seismic waves. These findings strongly suggested that the layer was not solid. Perhaps the lithosphere was isostatically balanced in this plastic layer, and continents could move around in it if a suitable power source existed. Seafloor spreading. The hypothesis of seafloor spreading is a new development which provides the theory of continental drift. The seafloor has a remarkable feature: an interconnected mountain chain that is reached some 64,000 km in extent and averaging 1,000 km in width. The concept of seafloor spreading was put forward jointly by the late Professor Harry H. S. of the Princeton University and Robert S. Dietz in 1960. The idea of seafloor spreading is a synthesis of the results obtained by marine geologists and geophysicists like Maurice Ewing and his co-researchers. Hess and Dietz proposed seafloor spreading as a mechanism that builds this mountain chain and drives continental movement. In the opinion of Hess, the submarine mountain ranges called the mid-oceanic ridges were the direct result of upwelling flows of magma from hot areas in the upper mantle and asthenosphere, and perhaps deeper source. When mantle convection brings magma up to the crust is fractured and the magma spills out and cools to form new seafloor, building the ridges and spreading laterally. The marine geologists between 1950 and 1960 had been able to establish the following three important facts about the floor of the ocean. The crust below the ocean floor was found to be only 6 to 7 km thick, whereas below the continental surface this thickness was 30 to 40 km. The existence of the mid-oceanic ridge was known to the geologists and geophysicists, but it was discovered that mid-oceanic ridges were present in all oceans. The ridges were subjected to earthquake and volcanic eruption. Third point, the rocks of the ocean floor nowhere were found to be older than the Cretaceous period, which began about 135 million years ago, while the Earth's age is 4.6 billion years. The youngest crust anywhere on the Earth is at the spreading centers of mid-oceanic ridges, with increasing distance from these centers. The Earth's surface is increasingly older. The older seafloor is the Western Pacific near the Japan, called the Pegafid Basin. On the basis of the above discovery, Hess proposed that the ocean floor was mobile and hot magma, that is lava, rises up from the Earth's mantle by convection currents along the middle of the mid-oceanic ridges and moves away on either side and finally get lost in the ocean trenches situated along the continental coast. It is through this process, the spreading, that the ocean floor has been built. In other words, the ocean floor is a relatively young feature of the Earth's surface. It is constantly being regenerated at the mid-oceanic ridges and is subjected to continuous lateral spreading until it is destroyed in the trench system and becomes reincorporated into the mantle. On the other hand, in spite of the fact that the continents are old and apparently permanent features, they drift apart passively and together on the backs of mantle-generated convection current. These facts prove that the continents and oceanic basin are in constant motion. Has put forward the following evidence and arguments in support of his theory of seafloor spreading. The occurrence of earthquake along the crust of the mid-oceanic ridges. The dearth of sediments at the crest of the mid-oceanic ridges and the active volcanic islands associated with the crest of the mid-Atlantic ridges are easily explainable in Hess' theory of seafloor spreading. Moreover, the thickness of the sediments increased with the distance from the ridges. This is inconsistent with seafloor spreading because the more distant parts are older and have had a longer time at their disposal to deposit sediments. The edge of the marine sediments above the basalt layer goes on increasing with distance from the ridge. For example, in the Atlantic Ocean, the age of the main sediments near the ridges was found to be less than 7 million years, while the age of sediment farthest away from the ridge has been calculated to be more than 1600 million years. There is a reversal in magnetic field of the Earth known as magnetic dipole. The normal and reverse magnetic anomalies are found in alternate manner on either side of the mid-oceanic ridges. There is a parallelism in the time sequence of paleomagnetic epochs and events calculated for about 4.6 million years on the basis of magnetism of basalt rocks or sedimentary rocks. Paleomagnetism. The study of rock magnetism developed during the 1950s with the perfection of new highly sensitive magnetometers. Certain rocks such as basalt are fairly rich in iron and become weakly magnetized by Earth's magnetic field as they cool. In the sense, the mineral grains in the rock become fossil magnets, oriented with the respect to Earth's magnetic field at the time when the rock was formed. Thus, they preserve a record of paleomagnetism. Similarly, the iron grains are red sandstone becomes oriented in Earth's magnetic field as the sediment is deposited. So, red stone also can indicate the orientation of the paleomagnetic fields. These rocks therefore retain an imprint of Earth's magnetic field at the time of their formation. Formation, a pattern of magnetic patterns of magnetic reversal on seafloor. Recent studies of the magnetic properties of numerous samples of basalt from many parts of the world demonstrate that Earth's magnetic field has been reversed many times over the last 70 to 80 million years. Epochs of normal polarity, that is, periods when the magnetic field was oriented as it today, and the magnetic poles were thus caused to their present location, lasting from 1 to 3 million years, have been followed by similar period during which the north magnetic pole and the south magnetic pole were reversed. At least 9 magnetic reversals have occurred in the last 4.5 million years. The present period of normal polarity began about 70,000 years ago. It was preceded by a period of reversal polarity, which began 2.5 million years ago and lasted 2 million years. That period of generally reversed polarity contained 2 short periods of normal polarity. The major intervals of alternating polarity, that is about 1 million years apart, are termed polarity epochs, and the intervals of shorter duration are called polarity events. In brief, a new crust is generated on the oceanic ridges and the seafloor spreads. Consequently, the alignment of the magnetic field in force at the time dictates the alignment of magnetic particles in the cooling rock, creating a kind of magnetic tape recorded in the seafloor. Each magnetic reversal and reorientation of Earth's polarity is recorded in ocean crust. Note the magnetic mirror images that develop on either side of the seafloor rift as a result of these magnetic reversal recorded in the rock. If you measure the same distance from the rift to either side, you find the same orientation of magnetic content in the rock. Thus, a periodic reversal of Earth's magnetic field have proven a valuable clue to understanding seafloor spreading. In a sense, scientists were provided with global pattern of magnetic strips to use in fitting together piece of Earth's crust. As the age of the seafloor was determined from these seafloor recording of the Earth's magnetic field, reversal and over circumstance, the complex harmony of two concepts of continental drift and seafloor spreading became clearer. The youngest crust anywhere on the Earth is at the spreading center of the mid-oceanic ridges. With increasing distance from the center, Earth's surface gets increasingly older. The oldest seafloor is in the western Pacific near Japan, an area called the Pangaea. Overall, the seafloor is relatively young. Nowhere does it exceed 200 million years in age. Remarkably, when you remember the Earth's age is 4.6 billion years. The reason is that oceanic crust is not permanent. It is slowly plunging beneath continental crust along Earth's deep oceanic trenches. The discovery that the seafloor is so young demolished earlier geologic thinking that the oldest rock would be found there. On the basis of the above evidence, it may be inferred that there is a continuous spreading of seafloor. New basaltic crust is continuously formed along the mid-oceanic ridges. The newly formed basaltic layer is divided into two equal halves and is thus displaced away from the mid-oceanic ridges. Alternate strips of positive and negative magnetic anomalies are found on the either side of the mid-oceanic ridges. Such magnetic anomalies, that is positive and negative, are found because of temporal reversal of geomagnetic fields. The rocks formed during the normal geomagnetic fields contain positive magnetic anomalies, while the rock formed during the reversal polarity denote negative magnetic anomalies. The seafloor spreading hypothesis explains a number of things such as continental drift, occurrence of earthquake near the mid-oceanic ridges, and the absence of sediments on their summits, presence of active volcanic islands on the mid-Atlantic ridges, the absence of rock older than 135 million years on the ocean floor on the oceanic islands. Overall, seafloor is relatively young. Nowhere does it exceed 200 million years age when the Earth's age is 4.6 billion years. The reason is that the ocean crust is not permanent. It is slowly plunging beneath the continental crust along Earth's deep ocean trenches. The discovery that the seafloor is so young demolished earlier geological thinking that the oldest rock would be found there. The concept of seafloor spreading is an increasingly convincing evidence about the continental drift. Moreover, the hypothesis of seafloor spreading has now developed into more sophisticated and comprehensive theory of plate tectonic, in the context of which the theories of continental drift and seafloor spreading appears to be obsolete and outdated. Plate tectonics. The term plate tectonic was first used by Tuzo Wilson of the University of Toronto in 1965, but the theory of plate tectonic was first published by W.J. Morgan of the Princeton University in 1967. This theory is based on the concept of seafloor spreading advocated by Harry H.S. and confirmed by Wayne and Matthews by their interpretation of linear magnetic anomalies. It is an improvement over the Wegener's theory of continental drift and has been considered as most sophisticated and comprehensive theory about the drift of continents and expansion of seafloors. Plate tectonics is a theory of global dynamics in which the lithosphere is believed to be broken into a series of separate plates that moves in response to convection in the upper mantle. The margins of the plates are sites of considerable geologic activity, such as seafloor spreading, volcanic eruption, crustal deformation, mountain building, and continental drift. Tectonic, from the Greek tectonics, meaning building or construction, refers to the deformation of the Earth's crust as a result of internal forces, which can form various structures in the lithosphere. Tectonics process include the upwelling of magma, plate movement, subduction of the crust, plus folds, faults, wraps, fractures, earthquake, and volcanic activity. Lithospheric plates. Plate is a broad segment of lithosphere which including the ridge, upper mantle plus oceanic and continental crust. Plate is the broad segment of lithosphere that floats on the underlying asthenosphere and move independently on other plates. La Pichon in 1965 divided the Earth into 7 major plates and 9 minor plates. These are as follows. Major plates, first one, African plate, second North American plate, third South American plate, fourth Antarctica plate, fifth Australian plate, sixth Eurasian plate, seventh Pacific plate. Minor plates are Arabian plate, Bismarck plate, Caribbean plate, Carolina plate, Cocos plate, Juan de Fuca plate, Nazca plate or East Pacific plate, Philippine plates, Scotia plate, Persian plate, Anatolian plate, China plate, Fiji plate. It is proposed in the theory of plate tectonics that the entire plate surface of the earth comprises of internally rigid but relatively thin plates, that is 100 to 150 km thick. These plates are continuously in motion, both with respect to each other and the Earth's axis of rotation. Virtually all seismicity, volcanicity and tectonic activities is localized around the plate margin and is associated with differential motion between adjacent plates. Most of the plates include both continental and oceanic crust. The area of the plates is fairly large in comparison to their depth and thickness. It has also been established that the depth of the plate is even less under the oceanic crust. Three types of motion are possible between the plates. First one, separation or divergent. Second one, closing together or convergent. Third one, friction or shearing. Plate boundaries are margin. Plate boundaries are lithospheric plates can be curved as well as straight, and individual plates can pivot as they move. There are many geometric variations in the shapes and motion of individual plates. The plates move at different rates. For example, the rate of movement is highest on equator and lowest on the poles. According to this theory, continuous sea spreading produces fracture on oceanic ridges and the Rift Valley, and magma from the upper mantle is injected into these fractures to become new oceanic crust. The convection current in the mantle carry the continents away from the oceanic ridge toward deep ocean trenches. There, the oceanic crust descends into mantle with the descending convection current and is reabsorbed. In this way, the entire oceanic floor is completely regenerated in 200 to 300 million years. First one, constructive plate margins or divergent plate boundaries. The plate diverge and move along mid-oceanic ridges. Hot material from the upper mantle swells up and fills the void. Some of this material is erupted at the surface of the basaltic lava. Thus, new lithosphere is formed at the plate drilling edge. The oceanic ridges stand high because their material is hot and therefore low in density. Heat flow at the ridge crest is 6 times greater than that of the old oceanic crust beyond the flanks of the oceanic ridges. New plates form and as old one breaks up and drift apart. The ridge represent a zone along which two plates are in motion away from each other. Yet they do not separate because new material is continuously added to the near of each. Thus, the mid-oceanic ridges on which a new ocean crust is being formed are known as the constructive plate margins. The Rift Valley of East Africa are believed to have formed along the zone of incipient divergent plate boundaries and are characterized by condemning rifting and volcanism. A more advanced stage of rifting is exemplified by the Red Sea, which almost completely separates the Arabian Peninsula from Africa, which, while most divergent boundaries occur in mid-oceanic ridges, there are few within continents themselves. An example is the Great Rift Valley of East Africa, Red Sea and Dead Sea, where continental crust is being rifted apart. The ridges are commonly offset by large faults that are also the sites of shallow earthquake. It is here that plates slide past one another. The best known example of this type of fault is California's San Andreas Fault. Next one, destructive plate margin or convergent boundaries. The second type of margin occurs in the deep ocean trenches. At the ocean trenches, two plates approach each other. One slips down under the margin of the other at an angle about 45 degrees. Thus, plate boundaries at which the net effect of the motion is to destroy surface area are called destructive plate margins. The process of subduction ultimately results in full mountain belts, alternation of the rock by heat pressure, and the growth of continent and oceanic basin. At the point where plates converge, one tips down and slides beneath the other, a process known as subduction. The simplest form of the convergent junction is one where two plates with oceanic crust meet. Such plate junction is the Eastern Pacific region lie along the volcanic islands Tonga, the Marianas and the Aleutians. A trench normally 5 to 8 km deep is formed where the underlying plate plunges down into the mantle. The subduction plate is heated as it tries to descend into the mantle and some of the material melts. The subduction plate is heated up as it tries to descend into the mantle, or some of the material melts, rises and may be extruded to form a string of volcanic islands or a chain of volcanoes on the continents. It is a series of these volcanic arcs that make up a ring of fire around the Pacific Ocean. In brief, crust is destroyed by convergent plate boundaries, region of violent geological activity where plates are pushing together. South America embedded in the westward moving South American plate encounters the Pacific Nazca plate as it moves eastward. The relatively thick and high continental lithosphere of South America rides up and over the heavy oceanic lithosphere of the Nazca plate, which is subjected into the deep trench that parallels the west coast of South America. Other examples are the area of the Japan and Aleutian trenches and the collision of Indian and Eurasian plates. The subduction plates periodic downward lurches causes earthquake. Some of the oceanic crust and its sediments will melt as the plate plunges down, forming a magma rich in water and carbon dioxide. In places, this magma rises through overlying layer to the surface and causes volcanic eruption. The active volcanoes of Central America and the South America's Andes Mountains are product of this activity, as these are the areas of numerous earthquakes. The North American cassettes volcanoes including Mount St. Helens result from the similar process. Most of the subducted crust mixes with the mantle, some of it eventually reaching the mantle to depth at least 400 km. Many island arcs are peripheral trenches of the western and northern Pacific Ocean, results from the convergence of two oceanic plates. Plate convergence is faster in the Pacific Ocean than in Atlantic Ocean, in a few places reaching at the rate of 18 centimeter per year. This is the source of Pacific Ring of Fire. The conservative Pacific plate margin or transform boundaries. These are the margins at which the plates neither gain nor lose surface area but simply slip past each other. This happens along the transform faults and thus the crust is neither created nor destroyed. Usually there is no volcanic eruption on transfer boundaries. The potential for earthquake may however be great as the plate edge slip past one another. The eastern boundary of the Pacific plate is a long transform fault system. California's San Andreas fault is merely the most famous of many faults marking the junction between the Pacific and North American plates. It is believed that some 50 million years from now, the Western California will encounter the Aleutian Trench. Main assumption of plate tectonics. There are three main assumptions of the theory of plate tectonics. The first one, that seafloor spreading occurs, that is, new oceanic crust is continuously generated at irregular line sources. That the area of the Earth's surface is fixed and during the last 600 million years, the radius of the Earth does not appear to have increased by more than 5%. In other words, the area of the crust destroyed almost equal of the Earth of new crust created. That once formed new crust forms part of rigid plate which may or may not incorporate continental material. Causes of plate motion. The main possible cause of plate motion are as follows. First one, thermal. Convection in the mantle is believed to be thermal. Convection in the mantle is believed to be the fundamental process responsible for the plate motion. All active oceanic ridges are characterized by a wider scatter of heat flow values, some of which are very high. With increasing distance from the ridge crest, the scatter diminishes and mean heat flow falls until it reaches average level for the oceans. On the other hand, oceanic trenches have abnormally low heat flow but a shorter distance away in the adjacent island arc. The flow is high. Rate of motion. Spreading occurs symmetrically at ridges at rates ranging from less than 1 to 6 cm per year. At oceanic trenches, crust is connected at the rate from 5 to 15 cm per year. Oceanic crust formation. Whatever the detailed process for crustal deformation at mid-oceanic ridges, it seems that crust is approximately the same thickness is generated whatever the spreading rate. Oceanic topography. The mechanism must be consistent with the development of topographic ridges at center of spreading. Ridges rise 2 to 4 km above the sea level of oceanic floor and near the axis slope away more or less symmetrically from the crest. Gravity. Observations show the ridges are close to isostatic equilibrium. Sinks are characterized by topographic trenches, which may to a greater extent be filled with sediments. They are strongly out of equilibrium and show the largest negative gravity anomalies recorded on the Earth. Distance separating sinks and source. This is highly variable. In some cases, newly formed lithosphere may travel only a few hundreds of kilometers before it consumed. In other cases, the sink may be 2 or more thousand kilometers apart. Strength of lithosphere. Even large lithospheric plates appear to be able to move great distance without undergoing significant internal deformation. In some cases, the plates are 20 times as long as they are thick. With such a length to thickness ratio, neither compressional nor tensional stress could be transmitted from one end of the plate to the other unless the frictional resistance beneath the plate was very small. On account of the presence of high heat flow near the ridges, several scientists have suggested that the movement of the surface is related to some sort of convection in the interior of the Earth. Recently, D.L. Turcotte and E.R. Oxberg have put forward the concept of thermal boundary layers based on thermal convection. On account of thermal instability in the mantle, heat is conducted upward through the movement of molten material. Once this kind of movement has started, the pattern takes to form the convection current. The thermal energy generated by convectional current is the main cause of movement of the major and minor plates. There is thus no lack of possible driving mechanism. Plates may be pushed apart by mantle upwelling, pulled apart by sinker beneath the trench system, carried by convection currents in the atmosphere and slide under the influence of gravity. Moreover, stress set up between and within the plates may be part determine their motion. In this picture, it is observed that most of the earthquakes and volcanoes of the world are found in narrow, semi-continuous but definite belts. These belts are of most part confined to the plate boundaries. In fact, seismic belts have been used as a basis for the delineation of plates. Seismicity is limited to mid-oceanic ridges, trench arc system, major fracture zone, and the young folded mountain belts, and all these features are indicative of plate boundaries. On all plate boundaries, and especially on the mid-oceanic ridges, shallow focus earthquakes are found, but intermediate and deep focus earthquakes which have their focus deeper than 200 km are mostly found within the oceanic trenches. This is the area where the plate descends starting from the surface of the trench to depth of 300 to 400 km, which may sometimes extend up to depth of 700 km. The inclination of this zone is towards the continental landmass, and the angle of inclination varies between 30 degrees and 80 degrees. Though in most case it is between 45 degrees to 60 degrees. Such inclined seismic focus zones are found near the entire Pacific coast. They are called the Benioff Zone or Pacific Ring of Fire, as the seismologist Hugo Benioff was the first to discover them. As a general principle, it may be stated that the Benioff zone is related to the downward motion of the lithosphere. On the basis of evidence from the seafloor spreading and paleomagnetism, it has been now validated that the continents and the ocean basin have never been stationary or fixed at their place. Rather, these have always been mobile throughout the geological history of the earth, and they are still moving in relation to each other. The scientists have discovered ample evidence to demonstrate the opening and closing of ocean basin. For example, the Mediterranean Sea, the Caspian Sea, the Aral Sea are the residual of one very vast ocean, that is Tethys Sea, and the Pacific Ocean is continuously shrinking and because of gradual subduction of American plate along its ridge. Contrary to this, the Atlantic Ocean is continuously expanding over last 200 million years. Red Sea has started to open. In the opinion of F.J. Vine, the Red Sea is spreading at the rate of 1 centimeter per year. Since the past 3 to 4 million years, the Gulf of Aden is also widening at the rate of about 1 centimeter per year. Baja, the Californian peninsula, was previously united with the mainland of North America but later on broke away from the continent due to spreading of seafloor. Moreover, the Bay of Biscay is shrinking. Next, plate tectonic and mountain building. The process of mountain building is known as orogenesis. The origin of mountain had been a point of great disagreement between the geologists and experts of geomorphologists. Some of the well-known scholars who attempted to explain the origin of continents are Hall, Dana, Hughes, Kober, thermal concentration theory of Jeffries, sliding continental theory of Dale, thermal convection current theory of Ohms, and radioactive theory of Joule. All these theories have almost lost their significance after the postulation of the concept of seafloor spreading by Harry H.S. and theory of plate tectonics by W.J. Morgan. The theory of plate tectonic was developed during the early 1960s when the new technological advancement and new instrumentation permitted scientists to map the topography of the ocean floor and to study its magnetic and seismic characteristics. According to the theory, the plate tectonic, the mountain building, takes place along the convergent margin of the plates. The characteristics of mountain belt and the sequence of events that produce it depend largely on the type of the crust carried on the converging plate and the type of sediments involved in the deformation. Three distinctive types of convergence are recognized. First one, the convergence of two continental plates. Second one, the convergence of a continental plate and an oceanic plate. And third one, the convergence of two oceanic plates. First one, the convergence of two continental plates. When two continental plates move towards each other, the continental plate having relatively denser material is subducted under the other continental material with relatively lighter material. The resultant lateral compression squeezes and fold sediments are on either side of the continental plate margins. The convergence of two predominantly continental plates generates an orogenic belt with several characteristics. The Himalayan mountains are example of orogenesis due to the continental collision. About 70 to 65 million years ago, there was an extensive geosyncline in the base of Himalayas. Tethys geosyncline was bordered by the Asiatic plate in north and Indian plate in the south. Next, convergence of continental and oceanic plate. When one continental plate and other oceanic plate collided to their when one continental and other oceanic plate collided due to their convergence along the subduction on Benioff Zone, the oceanic plate boundary became heavier in subducted below the continental plate. The sediments deposited on the continental margin are squeezed and folded due to the compressive forces. The convergence of the plate produces a mountain belt characterized by the fold dead sedimentary rock with the roots of granitic intrusion and metamorphosed sedimentary rocks. Next one, convergence of two oceanic plates. When two ocean plates collide with each other, the relatively denser plate subducts under the lighter plate. The density of the ocean crust depends on the proportion of silica and magnesium. The subduction portion of the plate after reaching about 100 km starts melting due to the high temperature prevailing in the upper mantle. Hotspots. The idea of hotspot was developed in 1963 from the observation concerning geology of the Hawaiian Islands. A significant aspect of plate tectonics is the estimated 50 to 100 hotspots across the surface of the earth. These are individual sites of upwelling material from mantle. Hotspots occur beneath both oceanic and continental crust and appear to be deeply anchored in the mantle, tending to remain fixed beneath the migrating plates. Unlike conventional current in the Lithosphere that principally derive plate motion, scientists now think hotspots are initiated by upwelling plumes that are rooted below the 670 km transition zone. Thus, the area of plate that is above the hotspot is locally heated by a brief geological time it is there. It is few hundred thousand or million years. An example of the isolated hotspot is the one that has formed the Hawaiian Emperor Island chain. The Pacific plate has moved across this hot upward erupting plume for almost 80 million years, with the resulting string of volcanic islands moving northward away from the hotspot. Thus, the age of each island or seamount in the chain increases northward from the islands of Hawaii. Iceland is also an example of an active hotspot sitting astride in mid-oceanic ridge. It is also the best example of the segment of mid-oceanic ridge rising above sea level. This hotspot has generated enough material to form Iceland and continues to cause eruption from deep in the Lithosphere. As a result, Iceland is still growing in area and volumes. The youngest rocks are near the center of Iceland, with rock age increasing towards the eastern and western coast. The idea of mantle plume is a simple but powerful concept. The concept of mantle plume complements the theory of plate tectonics in that it helps to explain many features of the interior of plates. In next class, let us study about rocks. Thank you.